Welcome everybody. We got an interesting question here. We expected to integrate integral 0 to infinity 1 negative e raised to the power of negative x divided by x raised to the power of 2 times dx. Now this can be a little bit challenging and we need to adopt some caution. So having mentioned that, let me just start off. So foremost, what I wish to do is I would like to rewrite this as integral 0 to infinity 1 negative e raised to the power of negative x raised to the power of 2 times 1 over x squared times dx. Now if you were to have a term like d of negative 1 over x and you wanted its differential, then I can rewrite it as d of negative x raised to the power of negative 1. Upon differentiation, I would get negative of negative 1 times x to the power of negative 2, which is nothing but 1 over x squared. So this has given me now the ability to rewrite 1 over x squared as d of negative 1 over x. Now I would like to take UV method. So I'm taking u to be as 1 negative e raised to the power of negative x raised to the power of 2 and dv to be as d of negative 1 over x. Now differentiating this would give me 2 times 1 negative e raised to the power of negative x multiplied with differentiation of 1 is 0, differentiation of e raised to the power of negative x is going to give me negative 1 times e raised to the power of negative x times dx. So this can be further rewritten as 2 times 1 negative e raised to the power of negative x, negative positive, so I get e raised to the power of negative x times dx, which can again be rewritten by distributing e raised to the power of negative x inside. This is going to be e raised to the power of negative x followed by a negative sign and e raised to the power of negative 2 times x times dx. So this is my du. Now coming back to dv, I need to integrate dv to get v, and that is going to give me v is equal to integration of d of 1 over x with a negative sign is going to give me negative 1 over x. So applying the formula, which is uv negative integral v du, I now have in place of u, let me just write it over here so that I can have a fairly large amount of space. So it's going to be 1 negative e raised to the power of negative x raised to the power of 2, and my v is 1 over x with a negative sign, so I place the negative sign here. Of course the limits are 0 to infinity. Now this is followed by a negative integral v du. So my v is negative 1 over x, so this will become positive, and I place the x here. My du is 2 times of e raised to the power of negative x, negative e raised to the power of negative 2 times x times the dx. Okay, so now having got that, I need to consider this first and apply the limits. So let me consider this. Consider 1 negative e raised to the power of negative x raised to the power of 2 divided by x. Of course there is a negative sign there, so I'll place a negative sign. Now this is actually heading from 0 to infinity. Now as x is moving towards infinity, e raised to the power of negative x will move towards 0 and 1 over x will move towards 0. So if you were to apply the upper limit, the first term will become 0, and that would leave us with the second term, negative of 1 negative e raised to the power of negative x raised to the power of 2 divided by x. Now for the second term, I need to move x towards 0. So if x is moving towards 0, e raised to the power of negative x will move towards 1. So this is going to give me 1 negative 1 divided by 0, which is nothing but 0 by 0 form. So that would mean I need to apply L'Hopital method. So I need to apply L'Hopital rule. Okay, to extract the limits. So I've got limit x tending to 0. I am just ignoring the negative sign. There's no point in placing the negative sign there. So this is going to be 1 negative e raised to the power of negative x divided by x. So I will evaluate the value and then place it over there. Right? So this is what I've got. Right? Is everything is okay? Okay, so okay, I just want to make sure that everything is fine. Okay, so far so good. Okay, great. So now this is got. So let me apply the L'Hopital rule. So L'Hopital rule is nothing but differential of the numerator divided by the differentiation of the denominator. So I differentiate the numerator. I get 2 times 1 negative e raised to the power of negative x. So this 2 negative 1 times differential of 1 is 0. Differential of e raised to the power of negative x is going to be negative 1 times e raised to the power of negative x divided by differential of x is 1. So this is 2 times 1 negative e raised to the power of negative x. This is positive 1 followed by e raised to the power of negative x. Right? Now if I were to apply limits now, APL stands for applying limits. Applying limits means as x is tending towards 0, e raised to the power of negative x will tend towards 1. So that would mean I have 2 times of 1 negative 1 times 1. So this is going to be 2 times of 0, which is equal to 0. Okay, so we are getting 0 there. So that would mean, let me go back to the limit. This entire quantity is annihilated and we are left with this quantity alone. So we have to integrate this. So let me go back and perform the integration. So this is what we have got at the end of the day, or I would say at the end of performing all these working. So now we have to integrate this. As I mentioned to you, integrating this is not going to be easy. So I would like to define a function. This is Feynman's technique. So let me define a function. So that function is going to be I of p is equal to 2 times integral 0 to infinity e raised to the power of negative x negative e raised to the power of p times x with the negative sign divided by x times the dx. Now we are interested when p is equal to 2, but we need to obtain the boundary condition when p is equal to 1. So this is going to be I of 1 is equal to 2 times integral 0 to infinity e raised to the power of negative x negative e raised to the power of negative x divided by x times dx. Now clearly if you can see e raised to the power of negative x and negative e raised to the power of negative x gets cancelled, giving me 2 times integral 0 times dx divided by x, which is equal to 0. So therefore I of 1 is equal to 0. So that is an interesting value. Okay, so having got that, let me move on. Now what I wish to do is I will apply the total differential of d over dp on I of p. That is equal to 2 times of d over dp integral 0 to infinity e raised to the power of negative x negative e raised to the power of negative p times x divided by x times dx. Now this quantity which you see here is totally bounded, right? And because of the fact it's totally bounded, I can push this inside d over dp, and when I do that, d over dp will become dou over dou p. Total derivative will become partial derivative. So dou over dou p of e raised to the power of negative x negative e raised to the power of negative p times x divided by x times the dx. Now x has got nothing to do inside the derivative, since the function over here, or we are differentiating with reference to p. So I can safely take that x out, but not out of the integral, place it within the integral but outside the differential operator's influence. So dou over dou p of e raised to the power of negative x, that's the first derivative, followed by dou over dou p of e raised to the power of negative p times x, okay, times dx. So you have a dx there. So this is equal to 2 times integral 1 over x Now dou over dou p of e raised to the power of x is going to give me 0 because we are differentiating with reference to p, followed by dou over dou p of e raised to the power of negative p. That's going to give me a negative, right? This is actually e raised to the power of negative px. So I need to place the x there, right? The x is over here. So if I were to differentiate that, coefficient of p is negative x, so negative x comes over there and followed by differential of that quantity e raised to the power of negative px times total derivative dx is there. Now this is equal to 2 times integral, negative is positive, so x times e raised to the power of negative p times x times dx. There is an x in the denominator, place that. Now clearly this x and x gets cancelled, giving me equal to 2 times integral e raised to the power of negative p times x times dx. Now if I were to integrate this, I would get 2 times integral of e raised to the power of negative px is e raised to the power of negative px. The coefficient of x is negative p, so this is what I get. This is equal to negative 2 times of p e raised to the power of negative p times x. But the most important thing is this is 0 to infinity. Limits are 0 to infinity. We need to use that quantity. So this is negative 2 times p. If I were to apply the limits 0 to infinity, the upper limit e raised to the power of, in place of x I substitute negative infinity, p stays there, followed by e raised to the power of negative, p stays there, x is going to be 0. Now when x is tending to infinity, e raised to the power of negative x will tend to 0 as x is tending to infinity. So the first term, this term vanishes, but this term will give me 1. So that would mean I have 2 over p, right? Negative will become positive. Now what is on the left hand side? On the left hand side you have I dash of p. This is what you've got. Now you need to get rid of this I dash. So for that you need to integrate. So if you were to integrate, the integration is the opposite process of differentiation. So I dash of p is integrated. On the right hand side it's going to be integral 2 over p times dp. So this, as I mentioned to you, integration is the reverse process of differentiation. So this is going to give me I of p. On the right hand side I would have 2 times of integral dp over p, which when you integrate you will get ln of p. Since it's indefinite integral, you have to add the arbitrary constant c. So this is equal to I of p is equal to 2 times of ln p plus arbitrary constant c. Now we have a boundary condition. What is the boundary condition? When p is equal to 1, I have I of 1, right? I of 1 is equal to 2 times ln of p is 1. So let me place that value, p is 1, and okay, p is 1 plus constant c. But just move up over here. What is the boundary condition we have got? We have got I of 1 is equal to 0. So substitute that boundary condition. So 0 is equal to 2 times ln of 1 is 0 plus arbitrary constant c. Therefore c is equal to 0. Now c is equal to 0. If I were to take this as a, therefore I can rewrite a to be as I of p is equal to 2 times of ln p plus 0. But we need p to be equal to 2. That is what is required. So when p is equal to 2, we have I of 2 is equal to 2 times ln 2. But what is I of 2? What is I of 2? Let me move up here. I of 2 is when the value of p is equal to 2, right? This is I of p. When p is equal to 2, that is what is required. So this is actually what is required. So let me just copy this and give the final solution. So this is actually defined. This is what is defined, and let me write that. Since I of p is equal to this. Therefore, when p is equal to 2, I of 2 is equal to 2 times integral 0 to infinity e raised to the power of negative x, negative e raised to the power of negative 2 times x divided by x times dx. This is I of 2. So substitute. So if I were to take this as b, so therefore b will be rewritten as 2 times integral 0 to infinity e raised to the power of negative x, negative e raised to the power of negative 2 times x divided by x times dx is equal to 2 times ln 2. Right? So 2 and 2 gets cancelled. This means integral 0 to infinity e raised to the power of negative x, negative e raised to the power of negative 2x divided by x times dx is equal to ln 2. Okay, so that is the final solution. Now let me give a check. I want to check if I have done everything all right. Okay, so that is the end of this particular question. Okay, so it appears to be all right. Okay, if you find any slips anywhere I have missed something, please put it in the comment box. I will rectify it. So thank you everybody. Until we meet again. Enjoy.